Here we study partial derivatives. So today's topic is partial derivatives. Partial derivatives. And in more detail, subtopics are following. So first we give the definition of partial derivative. Definition. Then this is first item. Second, geometric interpretation of partial derivatives. So geometric interpretation. Next, we define higher order partial derivatives. So third item is higher order partial derivatives. Higher order partial derivatives. Partial derivatives. Then we define smooth functions. So definition of smooth function. So item number 4, smooth functions. And fifth subtopic is max or min. So at a point of max or min, all the partial derivatives are 0. So the first item, definition of partial derivative. So let us start with the definition of partial derivatives. So definition. We consider a function if defined on Rn to real valued multivariable function if that maps a point x1 and so on, so n tuple xn to f of x1 and so on xn, and this is a real number, belongs to R. So let this be a function and a equal to some point in Rn, that is a1 and so on an belongs to Rn. Then for I belongs to the set 1 comma dot 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 n. So if the limit so the expression is limit f a plus t e I minus f of a over t. So here t is real number as t tends to 0, and so if this limit exists, if the limit this exists, then it is called the ith partial derivative of the function f at the point A. This is the point A. So if the limit this limit exists, then it is called, so it is means this limit, then it is called the ith partial derivative of the function f at the point a, or in other words, we can say the limit is the partial derivative of the function f at the point with respect to the ith component variable. So this is ith component variable xi. Okay, so here, so we have used ei, and this ei is the ith basis element of the standard order basis of Rn, that is e I equal to 0, comma, and so on, 0, comma, 1, comma, 0, and so on. This is 0, where the only at ith position, this is ith position, the entry is 1, and all other positions have 0. So this is ith position. And when this limit exists, then we have the we will use the following notation d I f, so d sub I f acting so at the point a, so this is equal to the limit f a plus t e I minus f of a over t as limit t tends to 0. Okay, so we label this as equation number 1, and suppose this is definition 1. This is definition 1. Well, now we move to the second sub-item, geometric interpretation of partial derivatives. Geometric interpretation. So consider f is function from R into R, real valued, and a equal to the n tuple a1 an belongs to Rn. Now we define a function g from R to, so real valued single variable function. So define g by g of x, this is equal to f of a1 and so on, a I minus 1, comma, x, comma, a I plus 1, and so on, a n. So this is real valued function with single variable. Then the ordinary derivative of g at the point ai, so that is g prime of, so g prime of ai. So this is the ordinary derivative of the single variable real valued function g at the point ai. So this is equal to basically the partial derivatives of f with respect to the ith component variable at the point A. So yeah. So now you know what is what is the geometric meaning of the ordinary derivative of g prime ai, that is the slope of the tangent vector of the graph of the function g at the point a I comma g of ai. So here uh, so therefore we conclude that therefore we conclude that the ith partial derivative of f at the point A is the slope of the tangent vector or the tangent line of the tangent vector to the curve obtained by which is the tangent vector to the curve that is obtained by, so the curve is obtained by the intersection of the graph of the function f obtained by the intersection of the graph of the function f, so g of f, and this is by definition this is equal to uh, x comma f of x, where x belongs to the domain of the function f, that is Rn. So intersection of g of f with the hyperplane, so note that this subset of Rn plus 1. So x belongs to Rn and fx belongs to R. So x comma the order pair x comma f of x. So this is basically element in Rn plus 1. So with the hyperplane, so what is the hyperplane? So h, this is equal to, this is defined by xj. This is equal to j when j is not equal to I. So you may denote it by h sub I. And more precisely, h is equal to h sub I. This is equal to the set of all points in Rn plus 1, that is x1 and so on, xn comma xn plus 1, such that xj equal to a j when j is not equal to I. And more precisely, this is equal to the points a1 and so on, a I minus 1, here x comma ai plus 1 and so on, comma an comma y, where x and y are in set of reals. Well, so therefore we conclude that the ith partial derivative of f is the slope of the tangent vector to the curve. So the curve, so the description of the curve is here. So the curve is obtained by the intersection of GF with HI. So where is the slope? So at the point, where is the tangent vector? So at the point A comma f of A. Okay, so at this point, so if this is the curve obtained by, so this is, if this is intersection of HI with G of F, and this is the point A comma f of A, then, and this is tangent vector T. So slope of this tangent vector T is the ith partial derivative di f at the point A. So now we move to the third subtopic, higher order partial derivatives. So let us start with a real valued function with multiple variables r into f, r into r, and so for j lies between, so j lies between 1 and n, we assume that the jth partial derivative of f that exists in Rn. So assume dj f exists in Rn. That is for every point in Rn, every point A in Rn, the jth partial derivative of f at point A exists. Then what we have, then dj f, so that is basically a function from Rn to R, where x maps to dj f at the point x. So this is again a function, and the ith partial derivative. So now if ith partial derivative of this function, if ith partial derivative of the function dj f exists at the point A belongs to, at some point A belongs to Rn, then we denote it by di, so ith partial derivative of the function dj f at the point A. So this we denote by dj comma I. So let me write clearly. So dj comma I f at the point A. And now we have a definition. dj comma I f at the point A. This is called the second order mixed partial derivative of f at the point A. So this is called a mixed second order partial derivative, second order partial derivative of the function at the point of the function f at the point A. And so similarly, one can define higher order partial derivatives. Okay, so the higher order partial derivatives of f, partial derivatives of f are defined similarly. So that is, one can define the sum k, the function f over so this is kth order mixed partial derivative, so over del x I1 some power, or maybe one can write yeah, del x I1, del x I2, and so on, del x ik. So this is the kth order, and at the point A. So this is the kth order mixed partial derivative of the function f at the point A. This denotes the kth order mixed partial derivative of f at the point A in Rn. Now here we have the following natural question. So question 1, when di comma j f at A equal to dj comma I f at the point A. So that is when the mixed partial derivatives can be interchanged. So one can interchange the order. Okay, so this is the question. So right now we'll not answer this question. So before that, before answering the question 1, so let me define what is smooth functions. So item number 4, smooth functions. So this is the definition. Definition 1, a real valued function with multiple variables. So f from Rn to R is called smooth if it admits continuous partial derivatives of all orders. So this function is called smooth if it admits continuous partial derivatives, of all orders. For example, so f of x comma y, this is equal to constant function, or you may take x square plus y square polynomial function. This is smooth. Okay, so now definition 2, a vector valued multivariable function, that is f from Rn to Rm. So here domain is Rn and codomain, that is Rm. So f has so f of x1 and so on xn. So this is equal to, so it has m many component functions, f1 of x1 comma and so on xn comma and so on. The mth component function is fm of x1 and so on xn. So that is, this is xn. That is the point x1 xn maps to f of x1 and so on xn, and which has m many components function. So these are f1 and fn. So fm. So a function f from R into Rm is called smooth, or let me check. So here the definition is a function is called smooth. So if it admits continuous partial derivatives of all order on the domain Rn. So here a function f from R into Rm is called smooth on its domain Rn if its component functions are smooth. If fi, so component functions are from fi from R into R, so real valued. Okay, so for I equal to 1 to m. So there are m many component functions. So if these component functions are smooth on the domain Rn, that is, it's equivalent to say that this is suppose Rn and this is Rm and this is by I, where I lies between 1 and m. So this is ith projection function. So here it is f. So this is the composite function by I composed with f. So if, and this is ith component function fi. So if these functions are smooth, then f is called smooth. Now the following theorem. So now consider the following theorem, theorem 1, and this answers question 1. It says that if, well, so I have not talked about, so in the previous definition, a function f from R into R is called smooth if it admits continuous partial derivatives of all orders. So that is, for every k, this mixed partial derivatives will exist on Rn, and so this is function from Rn to R, and that should be continuous. So that is the notion, continuous partial derivatives. So partial derivatives will exist and they are continuous on its domain. So now come to the theorem 1. If the second order mixed partial derivatives d I comma j f and the other one dj comma I f. So if this mixed second order partial derivatives exist and are continuous, so exist on some neighborhood of of the point A exists in some open neighborhood of A and are continuous at the point A. So these partial derivatives are continuous at the point A. Then we have di comma j f at A equal to dj comma I f at A. Okay, so this theorem answers question 1. So this is the condition. So they must exist in some open neighborhood of A, and they should be continuous at A. So this is the condition when they will commute. So we'll not prove this theorem here. So well, let us move to the next topic, 5 max min. So here we consider a function from a subset A of subset of Rn, and codomain is set of reals Rn to R. So f is defined on some subset of Rn to R. Consider and A belongs to interior of A. Interior of A. So by definition, so recall that interior of A is the largest open subset of A. So largest is the largest open set that is contained in A. Contained in A. Now we say that at A, the function f has a local max or min if there exists some open neighborhood, so ball with center at the point A and some small enough radius delta, so that this contained in interior of A. So if there exists some open ball with center at A and radius small enough delta greater than 0, such that f of A, so this is local maximum, so this is greater than or equal to f of x for all x belongs to the ball B A delta, or for mean f of A less or equal to f of x, so this is minimum, so this happens for all x belongs to B A comma delta respectively. Now we have the following theorem. So this is theorem number 2. So it says that let a subset of Rn if max or mean. So that is if local. If a local max or mean, a local max or mean of the function if from a to R occurs at a point a. So at a point a belongs to interior of A, then we have all the partial derivatives of f dj if at that point a results 0 for j equal to 1 and so on up to n. So all the partial derivatives are 0 at a point of local maximum or minimum. Okay, so here we prove this theorem. So proof of theorem 2. Let a equal to a1 and so on an belongs to Rn or belongs to interior of A. And interior of A, that of course subset of Rn, open subset of Rn. So this is open subset of Rn and A belongs to interior of A. Then there exists some open ball with center at A and radius some delta. So this is delta. And this is suppose interior of A. Then there exists delta greater than 0 such that, so this implies there exists some delta greater than 0 such that a1 and so on ai minus 1 comma t comma ai plus 1 and so on. So instead of I, so instead of I, let me use j, because here dj of f at a equal to 0. So here let me use j. So this is j. Okay, so a1 and so on aj minus 1 comma t comma aj plus 1 comma and so on a n belongs to the interior of A, belongs to interior of A. So there exists some delta greater than 0 such that these points are in interior of J for all t belongs to the open interval with endpoints at a j minus delta comma a j plus delta. So therefore this implies so let me denote this point as a sub t. So this implies f of a sub t is defined. So because a sub t that belongs to the domain of the function we have considered. So a of a sub t that is defined. So now we define a function. So now we define a function g from the open interval with endpoints a j minus epsilon minus the delta a j minus delta comma a j plus delta to r. So this is defined by g of t. This is equal to f of a1 comma and so on a j minus 1 comma t comma a j plus 1 and so on a n. Then we have g admits. So if f has local max or min, then g also has g admits local max or min at the point t equal to aj, and well, this function is defined by for every t belongs to, so the domain a j minus delta comma a j plus delta. So at aj, at t equal to aj, g admits max or min, and therefore we have the ordinary derivative of g at the point t equal to aj. This is equal to 0, and this is exactly the partial so jth partial derivative of f at the point a. So this is equal to 0. So this is what we wanted to prove. So this completes the proof of theorem 2. Now here we have the following natural question. So this is question number. This is second question. So the question is following. So what about the converse of theorem 2? So more precisely, so converse means let f is a function from Rn to R, so real valued multivariable functions, such that all the partial derivative dj f at a, this is equal to 0 for all j equal to 1 and so on n. So the question is, so does it imply if admits a local max or min at a? So this is the question. So answer of this question is no. So we need to give some evidence. So some counter example. Example 1. So here we give 2 examples. So first we consider f, a function from, so real valued single variable function, let's say f of t, this is equal to t power 3. So you may take t power n, where so n is odd and greater than or equal to 3. So here at t equal to 0, df dt at 0, this is equal to 0, but at t equal to 0, f has neither max nor min. Example 2. So here consider f function from R2 to R defined by f of x comma y, this is equal to x square minus y square. And here, so the partial derivatives, of f with respect to the first and second variables, so d1f at the point 0 comma 0, this is equal to 0, and which is equal to d2f 0 comma 0. But f has no local max or min at the point 0 comma 0. Local max or min at 0 comma 0. Okay, so we stop here.